Black Hole Lab by Jesus Science. So we're going to use Newton's second law to find the mass of the black hole. We're going to use the law of gravitational force in order to do this, which is just the net force being equal to the gravitational constant times the two masses divided by the radius squared. And obviously, Newton's second law is the momentum is equal to the mass times velocity. And this is very important right here. We're going to be using the motion of the star to find the mass of the black hole. So that's the introduction. So the procedure is we're going to use a GlowScript code given to us and insert our physics principles that we've learned. And then a model will then be ran utilizing our principles, and we're going to use the data from the model to calculate the mass of the black hole. So let's take a look at the GlowScript code and the model. So first, you're going to want to change. You have to change the seed. You're going to put in your email, but more importantly, we're going to insert the gravitational constant 6.7 times 10 to the negative 11th, the mass of the star, which is 2 times 10 to the 30th, and then the change in time, which is 86,400 seconds. And then we have some vector addition right here, and then we're utilizing that Newton's second law right here to find the momentum, right? So we're using the mass of the star times the velocities, and then we're doing some more calculations right here for Fnet, and then the change in momentum over the change in time. So something of note right here is the radius. So the radius is going to be equal to the position of the origin minus the position of the star. And then if we derive the gravitational equation, so we get this to find the second mass, which is the mass of the black hole, we do the magnitude of the net force times the magnitude of the radius squared divided by the star's mass times the gravitational constant. And so let's actually take a look at what this looks like. So in this model, you're gonna notice that the parallel component is always gonna be the parallel component of the net force is always gonna be parallel to the velocity, right, at any given point in time, and that the perpendicular component is always gonna be pointing towards the center of the circle, or at least it should. So in this model, you can see that it's not quite as different as they should be. It's not as parallel. The parallel component isn't as parallel to the velocity as it should be. Unfortunately, it's a little off, and then it kind of trails off the end a little bit too much. So this is most likely due to an error in my code somewhere, and that's unfortunate, but it's going to happen in these labs. So now let's actually take a look at the mass of the black hole. So let's go back here. So we're just going to use the gravitational formula again. And we're going to plug in all our values that we know. So the net force is equal to 9.69096 times 10 to the 28th. The gravitational constant, 6.67 times 10 to the negative 11th. The mass of the star, 2 times 10 to the 30th. And the radius, which is 5.00825 times 10 to the 12th. And we plug in all those values into the derived equation for the mass of the black hole. Then we get that the mass of the black hole is equal to 4.5019136 times 10 to the 25th. So that's pretty cool. So now, what does this mean? So how are the net force and its parallel and perpendicular components different from the rate of change and its parallel and perpendicular components? Well, that's just it. They're actually equal. So, and we know this based off of Newton's second law. The net force is equal to the rate of change, and this is true for its parallel components and for its perpendicular components of the net force and the rate of change of momentum. So what if the black hole whose mass you found was removed and a different black hole was placed in the same location? So since the star is only affected by the gravitational force of this new black hole, we won't be able to find a value for the mass of this different black hole because it's different from the old one, obviously. So and we're relying on the star's motion data, as I said in the introduction, to tell us the force that's being exerted by this black hole on the star. So if the motion is exactly the same, if it's not different at all, then we don't have a way of telling any difference between this new black hole and the old black hole. So there's no way of finding a new mass.